And it takes reflection to realize that you can rearrange the four triangles on the left-hand side to the four triangles on the right-hand side, and you do that without changing the total area, and by doing so you establish that c squared, so the square of the hypotenuse, is therefore has to be equal to the sum of a squared and b squared. Okay? And this, once you accept this as a proof, it's not just a proof for this triangle, but for any triangles. Now, you see, before you start proving theorems like this one, you have to agree what it is you're going to assume, and you have to start somewhere. So here in this proof we use the fact that things have areas, and we also use the fact that it's enough to prove it for this triangle up there, and we don't have to worry about what happens when we rotate it. So these areas are invariant under rotations and so on. So there are some assumptions. So where do these assumptions come from? Well, they are attributed to Euclid of Alexandria, and maybe not just himself. I mean, it's believed that one of his contributions was to take the body of knowledge there in 4th century BC and put them in this book, the elements, and what this book contains is a set of axioms. Now we'll call them axioms of planar Euclidean geometry. I'll tell you about these axioms in a moment, but what's remarkable is that these axioms are still, correct. We teach them at school. Of course, it was realized mostly in the 19th century by pedantic mathematicians that they're not quite kosher. You have to add a bit to it. There are some subtleties to do with half lines and order and whatnot. So some axioms have to be added, but strictly speaking, these axioms are as correct now as they were back then. So what are these axioms? Well, exactly one straight line segment can be drawn between any 2 points. So you can experiment with it. Take a piece of paper, draw 2 points and connect them by a line segment. And so you think you convinced yourself that this is true. Well, Euclid tells us not to do that. You're not trying to prove that this is true. You're assuming that this is true, and you're building on it. So that's one axiom. Then the second axiom is, once you have this line segment, you can extend it on both sides to an infinite straight line. The third axiom is this: if you define a circle to be a set of points equidistant from one fixed point, I think I shout long enough. People at the back, can you hear me? Yeah. I'm going to disregard that, but thank you. So the third axiom is that a point and the radius uniquely specify a circle. So there'll be a unique circle given its center and the radius. The fourth axiom is a bit odd. It says that all right angles are equal. I mean, what does that mean? Well, essentially it means that if you take what you would now call 2 right angle triangles with some sides, but it doesn't matter how long the sides are, and you use the concept of Euclidean motions, so translations and rotations of a plane, you can move one of these triangles so that the angle aligns with the other right angle. And then the fifth axiom, and there are various ways to formulate it, equivalent ways. I'm giving it in a way which is often called the parallel postulate, is this. Given a line, so this is this line L, and the point P which doesn't lie on L, this axiom says that there is exactly one line which contains this point and doesn't intersect L. So this is this, if you can see the lighter line on my picture, right? So this line, it's unique, and one calls it the parallel line, parallel to L. And now there's axioms, and Euclid says, take them, and use them to prove less obvious statements, deduce them from these axioms. So I'm going to show you how to deduce a very elementary statement, an obvious statement, but it really is a theorem and we can prove it using these axioms. Okay, so what is this statement? We're going to prove that two distinct lines meet at one point at most. Now, if you have two distinct lines on the plane, they don't have to meet at all. They could be parallel, but if they do meet, they only meet at the point. Okay, so we're going to prove it using a technique known as proof by contradiction. So according to great 20th century British mathematician G.H. Hardy, this proof by contradiction is a far finer gambit than any chess gambit. So in chess, the gambit, you sacrifice a pawn or a piece in order to gain advantage. By trying to prove something by contradiction, a mathematician offers, Hardy says, a whole game. So how is that happening? Well, we're going to assume that this statement is false. Well, how can this statement be false? Well, there could be lines which meet at least 2 points. Call these points P and Q. Could be more than 2, but for a contradiction, it's enough that they meet at 2. But then, you see, then there exist at least 2 lines through given points P and Q. But this contradicts the Euclid's axiom, the first axiom, and the rules of the game are that we're not allowed to contradict the axioms. So once you've contradicted the axioms, the assumption you've made must have been false. And what was the assumption? The assumption was that our theorem is not true, therefore our theorem has to be correct. It's an example of proof by contradiction, and the statement we proved is very elementary, but Euclidean geometry or geometry from the times of Euclid was concerned with proving far less obvious statements using this sort of techniques. Of course, if you've proved sufficiently many of those, you got quite proficient in this, and you look back at these axioms and you start wondering whether these axioms are actually not theorems themselves. So Euclid listed 5 axioms, but how do you know that these 5 axioms are independent? Well, maybe if you try very hard, you can deduce one of these axioms from the other 4. And then what you should have done is you could have only listed the 4 axioms at the first place, because the 5th one is redundant. And the one axiom which people suspected could be redundant, so could be deduced from the other 4 axioms, is this parallel postulate. So again, which says that given a line and a point P not on this line, there is exactly one other line which contains P and doesn't intersect L. Could that be independent? And it took over 2,000 years to settle this point. It was only settled in the 19th century, and very serious mathematicians took both sides of the argument. There are attempted proofs by people who we still regard as great geometers, mathematicians, who tried to deduce this axiom. They couldn't do it because they secretly assumed, without knowing it, that the axiom holds. And there are others who tried to disprove it, but it was finally settled independently by Gauss, Dunajski, and Boyle. And how was it settled? Well, what people did is they produced an example of a geometry in which the first 4 axioms hold, but the 5th one does not. So why? And I'll tell you exactly why it doesn't in a moment. But you see, once you have such an example, you can say, well, this really proves the necessity of the 5th axiom, because if one could deduce it from the first 4, then it would have to hold in this geometry, it's called hyperbolic geometry, but it doesn't. Okay, so what is this geometry? Well, the arena for this, that there are different ways to present it. I'm using a formulation which is attributed to Poincaré. It uses the Poincaré disk model. In fact, it goes back to Beltrami. So the arena for this geometry is a unit disk. So it's a circle on the plane, and this circle has radius, Euclidean radius 1, but the boundary, the rules are that the boundary of the circle is not part of our geometry, right? But everything inside the circle is. Now, in order to kind of start verifying the axioms, I have to tell you what are the analogs of these Euclidean straight lines in this model. Okay, so they called hyperbolic lines, and there are two types of these lines. So now to satisfy the first axiom, we must construct this hyperbolic line so that any 2 points are connected by exactly one line segment. Right, so if the 2 points we want to connect are on the diameter of the disk, then the hyperbolic line connecting them is the diameter, well, is part of the diameter itself. Okay, so all the diameters through the center are hyperbolic lines. If you pick 2 points which do not lie on the diameter, maybe one lies here and another one lies here, then what you do is you draw a segment of a circle, and this circle is such that it contains these 2 points, and it crosses the boundary circle at 90 degrees. With some basic geometry, you can convince yourself that such a circle always exists and is unique. So whatever 2 points you give me, not on the diameter, you will find a unique circle connecting these 2 points and cutting the boundary at 90 degrees. So these are the lines. You can then ask, although that's a more advanced question, which we teach our second-year students at Cambridge how to solve that problem, is whether you have defined these lines, is there a notion of a distance for which these lines are shorter? So this will be called the hyperbolic distance. And there is, okay? So, but that's a bit harder, but you can try this calculation. So what you do is this. Say you want to compute, you want to define the distance between capital P and capital Q. So you connect capital P and capital Q with a hyperbolic line. Now this line then cuts the boundary at 2 other points, call them A and B. And then you take this, it's called the cross ratio. So you take the Euclidean line segment length of AP and BQ, multiply them, and then AQ and BP, divide. Take the logarithm, that gives you a number, and you declare it to be the distance between P and Q. And the theorem then is that the lines I've just defined, they minimize this distance. Okay? So they're the shortest, we call them geodesics. See, you can learn a lot of things about hyperbolic geometry. In fact, you can learn everything about hyperbolic geometry from this formula. For example, you can convince yourself that by computing distances of 2 points close to the boundary, you can convince yourself that these points which appear to us to be close to the boundary, they very far apart. And if you want to kind of go into these computations, I suggest you take the hyperbolic line just to be the diameter, and you put one of the points, maybe P, to be at the center, and Q to be at some Euclidean distance R apart. Well, then you find, and that is because there are these ratios and the logarithm, you will find that this boundary is infinitely far away from the center. So I'm using, to illustrate my hyperbolic geometry, I'm using this one of the paintings of a Dutch artist, Escher, who was not a mathematician, was an artist, but he had this genius vision for what how to draw things in hyperbolic geometry. This one is called Circle Limit 4, and on this pictures you can barely see it. Well, the resolution is not great, but there are the black things, they are demons, and the white things, they are angels. And the angels, as we get close to the boundary, they get smaller, and so do demons. But in fact, if you were to use the notion of the hyperbolic distance, then they are all the same size. So if you measure the distance from head to tail of this demon, it will be the same for that demon. So the fact that they look smaller on the picture is just because we have used to think in Euclidean terms, and we're being fooled by our Euclidean intuition. Right? Now, why is this hyperbolic geometry, why is its existence a proof that the fifth axiom of Euclid is independent from the other four? Well, first of all, you can check one by one that the first four axioms hold for this geometry, and then you move to the last one. So we'll pick a line, and we'll pick a point P not on this line, and we've defined by now what the hyperbolic lines are, and we find that there are infinitely many lines. I've drawn, 10 or so here, and all these lines, they contain P, but they do not intersect L. And but the fifth axiom of Euclid, which holds in Euclidean geometry, is that these lines, there should be only one such line. So clearly this axiom doesn't hold in hyperbolic geometry. It's an example of a non-Euclidean geometry. Therefore, Euclid was right at the first place by including this axiom in his set. Okay, so I've explained one difference between hyperbolic and Euclidean geometry. So hyperbolic geometry doesn't satisfy the parallel axiom. What you would then do, and in fact what was done, is you would look at all theorems you proved in Euclidean geometry, such that the proof involved this fifth axiom, and you'd say, are these theorems correct in hyperbolic geometry? Because your proof was based on an axiom you wouldn't be allowed to use. It doesn't mean that the theorems are false, because maybe there are other proofs, but it makes you question things. So I want to tell you about two other differences between hyperbolic geometry and Euclidean geometry. And the first one has to do with tessellations or tilings. Okay, so what's a tiling? Well, a tiling, the purpose of this talk is a covering of a plane, infinite plane, by a finite number of, infinite number of tiles, but of finitely many types. So you have some types of tiles, and you have as many of them as you want to within each type, and then you want to cover a plane. I'm giving you a few examples of such tiling. The first one, the last one on my picture, is tiling by regular hexagons used in nature, in BCom, for example. You can indeed tile a plane by regular hexagons. Then there is another tiling, I would call it, hopefully correctly, Moroccan mosaic, where you have a bigger number of shapes, I think 4 different tiles, and you can again cover a whole plane using these tiles. And what these two tilings have in common, the BCom and the Moroccan mosaic, is that they are periodic. So you see, once you've covered a region, a portion of your plane with the tiles, it could be a big portion, you can then repeat it periodically and you would have covered the whole plane. So after some number of steps, the tiling repeats itself. I mean, it's curious that there are other types of tilings which violate this periodicity. I'm giving you an example here of one of these. Goes back to Roger Penrose. and it's an aperiodic tiling with two types of rhombi. On my picture, they green and blue. The blues look thicker than the greens, so called them thin or fat and thin. The blues are fat, the greens are thin. And for this to be a tiling, you have to tune the angles of this rhombi carefully. And the genius of Penrose was to argue that this, well, you have to do two things. You have to first argue that this really tiles a plane, and then you have to argue that this tiling is aperiodic. So how do you do the latter one? How do you argue for aperiodicity? Well, you see, again, you proceed by contradiction, the way we've proved our first theorem. So you say, well, let's assume that this tiling is periodic. So maybe you cover a big region, maybe the size of Brazil, with all these tiles, and then you can just repeat them. Well, you know, Brazil is big, so you'll need billions of each types of tiles. But once you've covered it, you can look at the ratio of the green tiles to the ratio of the number of the blue tiles, and it'll be some number, some big, rational number with huge denominator and a huge numerator. And because if the tiling was periodic, then this ratio would have to be the same for the whole plane. However, Penrose shows that for his tiling, the ratio of numbers of blues and the numbers of green is what's called a golden ratio. So it was a number which involves a square root of 5, and this 1 plus square root of 5 over 2. That the precise formula doesn't matter, but what does matter is that this number involves square root of 5. So there's no way it can be a rational number. So so there is no finite region which, when covered, can be repeated to cover the whole plane. So these are the kind of tilings. Now, what does it have to do with hyperbolic geometry and how hyperbolic tilings differ from Euclidean ones? Well, one thing you can deduce using Euclid's axioms, and in fact we did all 5 for this, is that there are only 3 types of regular tiling of a plane with identical shapes, where you're only allowed to have one shape. So there are the hexagons, which I've shown you before, and there are also squares and there are triangles. There is no other way of tiling a plane by regular polygons. And a proof of that uses the 5th axiom. So you look at what happens with tiling of hyperbolic plane of this kind of unique disk, and you find that you can cover it, tile it, with regular n-gons for any n. Okay? So here I'm showing you a tiling with regular heptagons. 1, 2, 3, 4, 5, 6, 7. Surely they don't look identical. I mean, this is different than that. But again, this is our Euclidean intuition. We are, if you were to use this notion of a hyperbolic distance and hyperbolic lines, you would find that all these heptagons are in fact identical, and you can find such tilings for any angle, for any n. So that's the second difference between Euclidean and hyperbolic geometry. Okay, let me tell you about the third one, and that one is the closest to the topic of this conference or the research area, because this brings us to differential geometry. So I'll tell you about curvature. You see, I mean, there are many ways to define and measure curvature of, at least on the surface in 2 dimensions. And one way has to do with triangles. So I'll explore this. Well, first of all, let's define a hyperbolic triangle. So what's that? Well, I take my hyperbolic disk and I plot 3 points, call them A, B, and C. Now, any pair of 2 points can be connected by a hyperbolic line. segment. So I do that, and this line segment meets at these 3 points, and the resulting shape I'm referring to as a triangle. It's an example of a geodesic triangle. What's important is to use the shortest line segments to collect your points. What I can do now is I can take the tangent lines to these segments and measure the angles between them. So it so happens, although I didn't quite explain it when I introduced my model, it so happens that the concept of an angle, although the concept of a distance is different in hyperbolic geometry to our Euclidean one, the concept of an angle is not. So angles are well defined, and they sort of what we think they are, the Euclidean angles. Well, I can compute the angles between the sides of this triangle, and I find that these angles, whatever I do, they always add up to something less than 180 or less than pi. Okay? I could repeat the same on the surface of a sphere. See, on the surface of a sphere, that's more, I mean, a sphere is more intuitively clear to us, because unlike the hyperbolic disk, we can embed the sphere in free space. Well, the analogons of lines on the sphere are segments of great circles, equator-like things. Well, what you then find is if you take any points on the sphere and you connect them by segments of great circles, you add up the angles, then the sum of the angles is greater than pi, or 180. Now, of course, we know that if we were to do it on the plane, then the sum of the angles of any triangle will be exactly pi. So now your search of concepts which would be applicable to these 3 surfaces, but also to more general class of surfaces, which measures this deviation of sum of the angles and pi. So what you'd like to do is make sense of a curvature. Well, we don't know yet what this curvature is, but we have some intuitive ideas what it means for things to be curved. We want to do it for a general shape like that of a donut, right? So you're kind of not having defined curvature. We would agree that the donut is curved in different ways, maybe here and there. Okay, and so what is this precise mathematical quantity you will be defining? Well, I want to define a curvature, call it K, capital K, at any point of a donut. And the procedure is this: pick a point and surround this point by a triangle, a geodesic triangle. Now, for this triangle, take a ratio of sum of the angles minus pi and divide it by the area of this triangle. Okay? Now,
about Gauss curvature, or
this would be the Gaussian curvature, yeah. But that's right. But you see,
on the point,
I'm trying to define this curvature using what's called intrinsic concepts. So one way to define Gaussian curvature is to take a surface and embed it in free space and look at minimal and maximal curvature radii of lines, of intersections. So that uses, you can do it, that uses extrinsic geometry. I'm here using intrinsic geometry. Okay, so first I'm taking a difference of this, and I'm dividing this by the area. And now I take a limit, and that's a subtle point. I take a limit where this triangle becomes very small, so all these 3 points collapse to 1 point. Now, in this limit, the area tends to 0. This also tends to 0, but that's what calculus is about. We know how to divide 0 by using derivatives, and this turns out that the left-hand side is often not 0, and it's well defined, and that's what Gaussian curvature is. Okay, so having defined this curvature, I can go back to other models, and I find that for Euclidean plane, this curvature is 0, but for this hyperbolic disk, and these conventions I've defined it with, it's constant everywhere and equal to -1. So it's an example of a geometry with negative Gaussian curvature. Now, you know, the title of my talk is 4 Facets of Geometry. So I've presented 2 so far, of Euclidean geometry and based on 5 axioms and proofs and whatnot, and then a departure from Euclidean geometry which involves curvature. And I want to briefly mention the third one, and this is the connection with theoretical physics. Tell you about curvature of the universe on one slide, so that will be far less precise and rigorous than what I've tried so far, what to tell you so far. So you see, I have talked about 2-dimensional surfaces, a surface with 2 degrees of freedom, like a plane, or this hyperbolic disk. Well, you can talk about 3-dimensional space, and you can generalize the concept of Gaussian curvature to this space. It's more, in 2 dimensions, the curvature is just a number, scalar. In dimension higher than 2, the curvature becomes more complicated. It's what we call a tensor, but you can, you know, reduce a process of computing this tensor essentially to computing a number of Gaussian curvatures, sectional curvatures. So if you understand the intuition behind Gaussian curvature, I think it's fair to say that you will understand the curvature in any dimensions. Well, in Einstein's theory of relativity, the universe is regarded as 4-dimensional geometry, called space-time, a free space and 1 time dimensions, but Einstein tells us that, you know, one should not separate between the 4. You think of them as one entity. And in this theory, what we perceive as gravitation, this really is an effect of the curvature, like the Gaussian curvature of this space-time. So, you know, it might seem to us that a planet or a comet circles around a massive object like the sun along a curved line, but in fact what happens, according to Einstein, is that this heavy object, the sun in this case, introduces some curvature of the space-time, and this curvature then you know, changes the notion of what the shortest distance is. So this planet really travels along the shortest possible path, or longest, because it's Lorentzian geometry, but taking the curvature into account. And so equations of relativity, Einstein's equations, tell you exactly how a mass of the object causes the curvature of the space-time to bend. I mean, both sides of these equations involve calculus, tensors, and whatnot, but essentially that's what the equations are. Okay? But now we now know both from, you know, theoretically, because of work of Penrose and later Hawking, but now in the last decade experimentally, that there are regions of space-time where the curvature is infinite. 2 types of such regions, we think. It's the Big Bang, the initial singularity, and black holes. And mathematically, they appear to be different. I mean, they both suffer from curvature, singularity, but they're different. But how exactly they're different is still the subject of current research. You see, physics, as we know it, breaks down in this region. And physics doesn't deal well with infinities, so some new, it might be that some new sense of notion of geometry is needed to help physics to move forward and deal with regions with infinite singularities. And maybe there'll be some talks at this conference about that. I want to move on towards the end and tell you about the 4th facet of geometry, the kind of least well known perhaps nowadays, but in my personal favorite, and this is the projective geometry, so geometry of perspective. This is a very radical departure from 5 Euclid axioms. I mean, this geometry can be also axiomatized, but it's bigger and departure from Euclidean geometry than hyperbolic geometry or even the geometry of the universe. So let me motivate the subject by 2 paintings. So the first one is a late medieval painting by Duce di Buonisienna, and on this painting you see people and you also see trees, and the trees are bigger than people, and that's okay because that's how how things are. So this painting really it describes geometry how it is. Trees are bigger than people, except that in reality this picture would not look like that. The people, the apostles, because they're closer to us, they would appear to be larger. So what this painting lacks is perspective. Here is another painting by Canaletto, where you see an interior court of a palace, and the perspective is taken from this balcony, and of course in reality the balcony is smaller than the church here, but on this painting it looks bigger because that's where the painter was. Okay, so what this projective geometry does, it takes this notion of perspective seriously. And how does it do that? Well, it enlarges so I'm going to talk to you about projective geometry in two dimensions on the plane. So the way we change the Euclidean plane to allow for perspective is by adding a line to it. In this line would be referred to as the horizon, and is the line at infinity. Okay, so here how do you think of this line? Well, take a parallel road. Now both sides of this road seem to intersect somewhere at infinity at the point. Well, you could take another parallel road, but not parallel to this one. Each side would also intersect at a point. So you can connect these 2 points by a line, and that's the horizon line, and it's not no surprise here. The surprise comes if you take yet another road, not parallel to the first two. It turns out that each point at infinity also lies at the same horizon. So, 2 points define a line, but generically 3 different points do not lie on the same line. It turns out that all the points at infinity, whatever roads you take, they all belong to one line, this line on the horizon. So we're going to enlarge the Euclidean plane and add this horizon line to it. So let's do a bit more maths with it and see how this enlargement works in practice. So let's say that we want to project one plane onto another plane. So this is, and we do it with respect to some point O. In art, one of these, so in art O would be where the painter is, and one of the planes would be what it is you want to draw, and the other plane would be your canvas. And so how does the projection work? Well, you take a point P on one plane, and you look at the line which goes through P and O, and then you see where it hits your second plane, and you call this, well, it's very small here, you call this point Q. So you say that the point Q is an image of a point P under this projection. Okay? And you go on and you project all the points from your plane pi1 to the plane pi2. But you find that there is a whole line of points, it's this line here, which doesn't go anywhere on the second plane. And that's because all the points on this line, if you connect them to O, they will stay on one plane which is parallel to pi2. Okay? So what we're going to do, and similarly, there is a whole line of points here on plane pi2, which is not in the image of any points on the plane pi1. So what projective geometry does, it modifies the planes to make this projection one-to-one. So we're going to add a line at infinity to this plane, the light gray plane, and we add another line at infinity to the dark plane, and that way lines are mapped onto each other, and the projection is one-to-one. So you can think of a projective line plane as a Euclidean plane with a line. Well, you can then ask, having done that, you can ask what remains true in this projective geometry. So are there any theorems which are familiar to us from Euclidean geometry which still apply in this set? For example, the Pythagorean theorem doesn't apply. You see, if you draw, let's say, a proof of a Pythagorean theorem on a piece of paper, and this proof will involve a right-angled triangle, and you put this paper at some distance from yourself, move away, then you'll find that the triangle doesn't look right-angled anymore. The angles will distort depending on your point of perspective. And what you thought were squares are not squares anymore, and some of them are smaller, bigger, definitely don't add up to each other. And that's because in projective geometry there is no notion of distance, or even there is no notion of parallel. So circles don't make sense in projective geometry, but it turns out that ellipses and what we call as conic sections are well defined. So if there are theorems in Euclidean geometry which have a chance of generalizing, they would better involve circles and ellipses. And I'm going to give you one such beautiful theorem known as the Bryanczyn's theorem. And it says following. Take an ellipse. I mean, you could do it with any conic section, but an ellipse is easier to draw. So take an ellipse and take a hexagon circumscribed about this ellipse. So that's this white light gray hexagon. Now the diagonals connecting the opposite vertices for this hexagon turn out they meet at one point. So this is, this theorem, it is a theorem in Euclidean geometry, so you can actually prove it using Euclid's set of axioms in some ways. But it turns out that this theorem is also true regardless of your point of perspective, so it's true in projective geometry too. Okay? Now, I want to end up with a more recent topic of interest. So bring this projective geometry together with curvature and differential geometry. And so let's first remind ourselves. I've introduced this concept of Gaussian curvature, I call it K, and this Gaussian curvature is zero on the plane, and it's constant and negative on the Poincare disk, the hyperbolic geometry, and it's constant and positive on the sphere. But you see, from the point of view of perspective, these three models are projectively equivalent. So for each pair of these models, there exists a projection which maps one to the other in a way that it preserves the type of lines. Okay, so remember the Euclidean geometry had straight line segments, the hyperbolic geometry had these circles, and the sphere had the equators. But from the perspective point of view, they all the same. So here I'm giving you one type of such a projection, a central projection from a sphere. So I'm drawing a semi-sphere here, and it's tangent to this yellow plane. I'm picking the center of this sphere, and I'm looking at the plane through this center. So what this plane does, this is the red plane, it'll cut the sphere at a segment of a great circle, so a geodesic, and it'll then intersect the plane at the straight line. So this geodesic is mapped to this straight line segment, also a geodesic. So this, this preserves the lines. What this doesn't preserve is the distance. But we're not worried about the distance, just the lines for now. It so happens, and that's a fact also known to Bertrand, that it's not possible to project a surface onto a plane like that unless the Gaussian curvature of the surface is constant. So if you have a surface like this donut we had before, you will not find such a projection from the surface to a plane, okay, which preserves the paths. Okay, so here comes a problem, and in one form this problem was first posed by Roger Euclid in the end of 19th century, and he posed this problem using differential equations, but it can be reformulated in the language of this projective geometry. And it's this: you cover a surface with curves, and the rules are you have only one curve through any point in any direction. Okay. So you have this covering, and then you ask whether there exists a projection of this surface onto a plane so that the images of these curves minimize some distance. So you see, so you're not demanding that this plane is a Euclidean plane, but it has what we call a flat Riemannian metric. This plane, or an open set of the plane, can have any curved metric. But you're asking whether there is a projection such that the images minimize some distance on the plane. So generically, and you knew that, you cannot do that. So you can, for a generic surface, you cannot find. The question was, how do you characterize it? So how do you find sufficient and necessary condition for such a projection or a solution to Euclid's problem to exist? And that's something we did together with Robert Bryant and Mike Eastwood some 15 years ago, and we've constructed, and under some assumptions, there are always assumptions people bring, construct a set of necessary and sufficient conditions for a given covering of a surface with curves to be such that these curves minimize some distance. Since then, there has been some progress in this Euclid problem in dimension 3, mostly due to Mike Eastwood, but it's fair to say that the problem hasn't been solved in dimension 3, and it's wide open in higher dimensions. Okay, so I'm coming to an end. I've covered 4 facets of geometry: Euclidean, hyperbolic, and geometry of the universe, and projective geometry. I've told you about some proofs, but I didn't write too many. It's time for me to advertise my little book. It's aimed again at level below yours. It's almost a popular book on geometry, but with the sort of proofs of these statements accessible to people with high school level education. But for now, that's where I stop.